Yeah, it should start recording. Okay, so let us start. So what have we seen yesterday was basically a sequence to sequence problems or used in as so yeah, I think it's not commented. Yeah, so the structured predictions, the basic neural language models, and so on. Then we actually stopped at a very important question, the bottleneck problem, that actually in the encoder decoder architecture that we discussed yesterday, the basically all the information about the source sequence, that is everything. If it is a very long sequence that you need, that is your source sequence, that is, say for this language translation model, say that is the source language sentence, then everything about it has to be contained or sort of summarized in the last hidden state of the sentence. So here, so it needs to be contained there, and from that the decoder needs to figure out, okay, what is the subject, maybe what it is referring to, a particular word, what follows the subject, which verb is say following or connected to the subject, and something similar to this. So but this may be a daunting task if it is a very long sequence, and if the decoder does not have any way to basically peek into it when it is required, or maybe after a few steps of decoding is done. This it will help if the decoder can peek into the input sequence time and again during decoding. So we stopped at this point. How can we do it? So it will help to, when it is decoding, to have a look at say all these portions here for these etc. Okay, now let us go to how can we do it. So can we peek in the input? So this is first I will sort of outline how it is done. It may seem a little arbitrary at this point, but as we go along, it will be becoming more and more clear. And once we say give the more precise formulations, mathematical formulations, that will be even more clear. So what it does is that this is say let us take our encoder decoder model. Once or when we are encoding, we actually output some small piece of information which are called key vector. So this is key vector. So this key vector actually basically represents what type of information is present at that step during the encoding time. So it may not be very semantically meaningful to us if we think about it. So in isolation, it may be just some vector, but it can actually encode what type of information at this time step the source sequence is representing. It is learned in the form of a function. It can be, for example, a linear layer followed by a ReLU. It can be any function, but just a functional representation of these h's. Okay, so it is learned from the hidden state via some function. So this is the idea of the key. So just remember that, I mean, key vector represents the type of information that is present at that step during encoding. Now during decoding, for each time step, there is a query vector, and that represents what we are looking for at that step. So this is the query vector. So the idea is that, okay, key vector encodes what are the information that is present in each of these time steps, and query vector at a certain during decoding, query vector at a certain time step, say it has already produced the first two words, then here it might require some information from the past means here from the source sequence. It will just express its willingness that, okay, I want this information. So again, this is a high level intuition that I'm trying to give, but when you say see these vectors, it might not mean anything to you. So but it I mean, that is the idea behind, okay, why we can go for this key query type of architecture. So query vector represents what we are looking for, and key vector represents what type of information is present at the step in giving the encoder. So you need to sort of next you can guess that you need to give some interaction between key and query, so that the query gets what it is asking. So that is what is done then. So here that a query is compared with each key to find the closest one. So what does that mean is basically, you see, this is an information, the key gives the information that is present in the encoder, and I mean encoding step, time step, and query is looking for some information. So you need to query these informations given by the key. So you are basically telling that you compare the information that it is seeking and the information that the keys are providing, and you find the closest one, the one that is sort of you can think that answers the query. Okay, this tells which time step in the input is most relevant to the time step in the decoding process. So some information it is looking for, and this in principle, the similarity score computation or finding the closest match in the key, this gives that okay, at this time step maybe the input is most relevant to what the query is looking for. So this is again the high level idea going on. So let's say the this second time step, as I was saying, that that is probably the most relevant one. Okay, the information that is given, maybe this word is something it is looking for, that okay, what is following this a word, or here what is following this un word. Okay, so the corresponding hidden state is sent to the decoder. Now corresponding hidden state means this hidden state, this h corresponding to this. Okay, so that it processes. Now again, this crude intuition, as I was always telling, key might encode the subject of the sentence. Okay, this is the subject, say it is just or not subject, I mean, or not this case, maybe this one is it is encoding that okay, this is the subject of the sentence in the source language, and query is actually looking for what is the subject of the sentence. Or maybe that the key is telling okay, what the subject is doing, what is the activity or the verb corresponding to the subject, and query is maybe looking for that activity. And so on. And as I said, maybe query is looking for okay, what follows the article. So you I mean the key maybe encoding that at certain time step. I mean this may be this one. So the key encodes some information and query is looking for some information, and there are so many information, so you need to basically find which one of the keys are most relevant to the query. And what keys and queries mean is learned. So that is the thing. I mean, we do not specify it, as I was saying, for these intuitions that okay, this may be the subject of the sentence, etc., etc. We do not specify it, because that is not our job. So that's sort of the job that is of the model. I mean, this machine learning model. I mean, whatever is required, you try to express in terms of key and whatever query, and whatever is there that is present, you express in terms of key, and then you compare. So we do not have to select it manually. Now let us see how we do it actually in terms of mathematical formulation. So yeah, so this is okay, let's go. Okay, so we will basically denote this letter with this letter H and S, the hidden states of the encoder and the decoder. So we were denoting the hidden states of all these sort of time steps by the letter H, but just so that we don't confuse between the encoder hidden state and the decoder hidden state, we are just differentiating this by the two different letters. One is H for the encoder side, and S for the decoder side. So nothing I mean is different, just other than the notation. So what it means now, okay, so what it does now is that this key, it generates this key during the encoding. So key kt at each time step t is some learnable function of HT. So key is a function of HT, and that is learnable. I mean, we have seen some, many learnable functions that is used in, say, deep neural networks or connates. So KT is sigma, sort of rather linear layer followed by the sigmoid layer, some non-linear. It can be ReLU even, or some other functions, form of functions. So a very simple choice is this, and sometimes, most of the times this often does the job, correct? So you are when going from this hidden state to this hidden state, next hidden state, you also do a similar thing, right? So you do a linear transformation of the HT, and you basically pass it through a non-linearity. Same thing you do it here, but these are different W's and B's. So here maybe it is some WH, BH, and here it is this WK, BK. So just a different representation of the same HT. One gives the next hidden state, another gives this key. Okay. Now, similarly, the query QL is some learnable function of decoder state SL. So here, one important thing again, I've changed the notation a little bit again just to avoid the confusion. So L is now my times index for the decoder. So by T, I am using T for indexing time in encoder side, and L for indexing time in the decoder side. As well as I am using H to denote the encoder hidden state, and S to denote the decoder hidden state. Okay. So QL similarly, as K was a function of H, similarly Q is a function of S, and similarly, it's a very much learnable function. Example is again like this. It can be like this. All these values will be different. W will be maybe WQ, B will be BQ, HT in place of HT, it will be SL. Okay. Now you basically, after you compute, you have during encoding you have computed all these keys. Now during decoding, once say you are in certain state is certain time step is L, then you will have this query corresponding to L and all these KTs. So K1, K2, K3, and this S2. Okay, so you basically compare with, they compare this Q. Sorry, I said S2 probably. It is Q2. So Q2, you compare Q2 with K1, K2, K3, and this is what you get. So we call it as attention. This measures the similarity between the key and the query and is given by the dot product between them. So it is a form of a cosine similarity. Sometimes it is also called cosine similarity, but you can just think that it is a dot product. Cosine similarity it is called when the vectors are normalized to 1. Otherwise, generally the more general term is dot product. So intuitively, we want to pull out the hidden state HT for the time step T at which ETL is the largest. So at which the similarity is largest for which T. So for this L is fixed. Okay. For this L, we want to find the corresponding T where the similarity is maximum, and we will just send that HT because that is the most relevant one. So instead of always sending this H3 or a function of H3, which say is a linear function followed by sigmoid here and a linear function followed by sigmoid here of this last H3, that was ultimately used here to get this H2, right? H2. But now what it is saying that, okay, we will not only rely on this thing, but also we will rely on the most relevant H. So this directly this will go here. So this way, this is the idea that, okay, you measure the similarity, the corresponding hidden state at that time will be your most relevant. It can give you some additional information to decode at this, to get the output at this second time step during decoding. So that is what I mean when I say that intuitively we want to pull out the hidden state HT for the time step T at which ETL is largest. Okay. Now, so that is sort of mathematically expressed it as you get all these ETL, that is over T, argmax over T. So T, remember, T is for the encoding side. For a particular L, you are trying to find which of these time steps in during the encoding or which of these encoding time steps is most similar to this query. So you get that by doing this argmaxing over T of this ETL. ETL, remember what it was? It was the dot product. Okay, and send the corresponding HT to decoder at time step L. Okay. Now the thing is that argmax is not differentiable. Now, if it is not differentiable, what can be the problem? The problem is that it will break the back propagation. So because you are ultimately learning it, right? So it will break the back propagation if it is not differentiable, any function. So argmax function is not differentiable. So we will not be able to train the network. What we use is a softened version of this argmax, which is just our good old friend softmax. So what do you do? Instead, I mean, you take all these ETLs, that is E1L, E2L, and E3L. So E1L, E2L, and E3L, and for each of them, you divide it by the sum of these E1L, E2L, and E3L. So that way, you basically make it a probability distribution, sort of alpha TL gives you the similarity score, but now scale between 0 and 1, and the sum of the similarity scores will be 1, right? And it is, why is it a softened approximation? Because if you see that if one of them, I mean, ETL for a particular T, if that is say hugely high, comparatively very high compared to the other T's, or compared to the other ETL, compared to the ETLs for other T's, then it will be the corresponding alpha TL will be high and the rest one will be very small. So as you have one single highest score, it will sort of tend to the hard max or the argmax. But it I think the advantage is that since this has with these small values for every other T's, it will not break your and it has a very good sort of derivative with respect to its arguments. So it does not break the back propagation chain. Okay, so that's the advantage, and that's why it is a softened version. So as you have relatively high, single high component out of the components of softmax, it will tend more close to the hardmax or the argmax. Okay, so this is what you get. So the alpha L's, and send this alpha. I mean, now what you do is, instead of sending the HT corresponding to the max one, you just wait. You take all HTs and weigh these HTs with the corresponding alpha TLs. So remember what is alpha TL. Just try to sort of think it from the first principle. ETL is the similarity of the query at time L and key at time T, right? Now, what we were actually wanting is that the T that corresponds to the most similar key, or the time step that corresponds to the most similar key to the query, we would have sent this HT ideally, that corresponding HT for the decoding. But what we are doing is that, okay, I mean, since that argmax is not differentiable, we have approximated with this softened version. And softened version is nothing. I mean, this it has sort of one-to-one correspondence to this ETL. These alpha TLs have one-to-one correspondence to this ETL. So if the if ETL is high, then alpha TL is also high. If ETL is low, alpha TL is low. So you take these corresponding alpha TLs and the HTs, you weigh them, you multiply the alpha TL with the corresponding HTs, and then sum them. So you take a weighted combination. Instead of just taking one HT that is giving the full weight to that corresponding T that has the highest similarity, you are taking a weighted combination, and the weights come from these similarity scores. Okay, that you then send, that is called the AL, and that is sort of the attention. Why it is called attention, I'll just tell in a bit. So this AL, these are small numbers. Sorry, these alpha TLs are small numbers except for the max ETL. That's what we told now. So this AL then, instead of sending just the HT corresponding to the max ETL, you send this weighted combination of all the HTs weighed by the similarity score between the query and the key. That is sort of the most close approximation to the HTL in a differentiable way. HT corresponding to the largest ETL in a differentiable way. Okay, I am seeing some question here, so let me stop and ask. Okay, yeah, I have asked you to unmute. Yeah.
Yes, sir. Sir, one basic question. I think this is showing the language translation model. So acute puppy, it shouldn't it be the output? I mean, it's showing as the input to the decoder, but shouldn't it be the output from the decoder?
Yes. Yeah. That's a good question. Actually, I probably should have just got rid of this. I mean, the cute puppy thing is already here. I mean, it is like A is here, cute is here, and then A is coming there, cute is coming there. So I have got rid of this thing just to declutter, but I should have gotten rid of this also. But yeah, this just reminds you that it's a sort of autoregressive model that we discussed yesterday, that you are, I mean, the output here should, or maybe output here should also depend on what it has produced earlier. So just to remind you that. But yeah, I think for this purpose, I mean, just focusing on attention, maybe this could have gotten rid of.
Understand, sir. Okay, thank you.
Okay. Yeah, you can unraise your hand. Okay, now let me go to this one. Yeah, so we have said that, okay, we are computing this AL and we are basically sending it to the decoder. Now, what does send mean? That I have just sort of cleverly avoided, but let us discuss about it. So what does send mean? One way, basically send mean that you have to use it in some way. So what can be one way? That, okay, you are you will have to, or earlier in the encoder decoder net framework, without this key query, what you are getting here, as I was telling, just to address the question, you are getting the output here, and that output was also a function of only the hidden state of this decoder, which I was denoting as H, but now, as I said, to basically reduce the confusion between the encoder and decoder step, I am sort of denoting it as by S. So it was a function of then only S2. What we can do is that we can, after computing this AL, we can give this, sorry, not here, AL as an input to here also. So instead of only FSL, it is, the output is also a function of AL. So that is one very basic way of using it, that okay, the most similar hidden state, or now a softened version of it, that is a softmax version of the, or the weighted combination of the encoder time steps, encoder hidden states, also influences the output in addition to the hidden state of the decoder. So in addition to the hidden state of the decoder, all the hidden state of the encoder weighted suitably by the attention scores is giving you the output, not just SM. That is not just the decoder hidden state. That is one way. Then another way is giving AL to next RNN layer if stacked RNN is used. So we have seen how stacked RNNs are used. So you have these stacked RNNs there or there and so on. So you can give this as an input, maybe not as output, but I mean not during getting the output, but this AL you can give here, that AL you can give here, and so on. I mean, it also comes from the stacked RNN from the previous time step, but I mean, you can understand. I mean, all these, I mean, this RNN layer gets the, I mean, you compute the attention corresponding to this layer at this time step, you give it as input to the next layer at that time step. You compute the attention at this layer in this time step, you give it as input to this next layer at the same time step, and so on. So this we will see in following follow-up architecture. I mean, some sort of this a variant of it in when we discuss about transformer, sort of elegant architecture based on attention, so to say self attention, that we will discuss today, and use it in a layer wise form. So that we are not discussing this much, we will be discussing it there. Now append, yeah, so another way is to append AL to the next decoder step, SL bar. So previously this is how we were getting the next decoder step. Suppose this S2, it was a function of Y2 or yeah, sort of, yeah, I mean here it is Y2, but in general, since we tell it as I mean X, denote input as X, I have just given XL, but it was a function of the input at that time step. What I mean by this is that input at the time step and the previous hidden state from the decoder. In addition, you are actually giving the attention coming from the previous time step. Okay, so that way we can use this, and this is what we mean by sending attention to the decoder. I will come to the attention walkthrough. So what have we discussed till now is the outline of how attention works, the key query vector, what they represent, and so on. Then next we sort of given the mathematical formulation, and now we will go through an attention walkthrough example. But before that, I see raised hand for a long time. I'm asking Rishabh to ask your questions.
So can you move to the slide 59?
59.
Yes, sir. In this case, initially first we will calculate the attention, then after that we will calculate the output of S2.
Yes.
So, but
you will compute the attention, and then you will send it to the decoder. And by sending, I mean, what I tried to explain here is what you can actually do after you compute the attention. So
like initially when we are generating the query output, that time we won't consider the output for YH2. We will use it for the, so like when we are generating the query QL, we won't use it to generate the output. In fact, we will use it to generate the attention, and then after it will be connected to the S2, then we'll generate the output YS2.
Yes. So when you are generating the query, you are not directly using the query for the output. You are using the query for querying rather. Okay, so you are using the query to for querying the input hidden states. Okay, or encoder hidden states. You get some similarity. You combine the hidden states input or encoder hidden states with these weighted by this similarity, and you get one vector which is of the same length as these HTs, because you are sort of so where was this attention was computed here. So you are actually, these are scalar values. Remember, these alpha TLs, these are coming from ETLs, and ETLs are basically cosine similarity. So it's one single scalar value, and alpha TLs are again a single scalar value, right, for 1T and 1L, right? So when you are combining them, so ultimately this output will be of the same dimension as the hidden state. So this send it to say, by sending I again mean these many other variants, but these are just three options how you can use it. Okay,
and then for generating the YS2, the output of S2, we have to wait for attention. So in case of RNN, we don't have to wait, but in this step we have to just wait for the attention to come, and then
that is true. That is true, but there when we discuss transformer, you will see that actually you don't have to wait for it. It's parallel computation, or everything will be done in parallel. Here, of course, the recurrent connections are there. It may not make sense at this point. What do I mean by that? Okay, recurrent connections are there, in transformer it will be not there, but we will be discussing it today itself. Okay. Yeah, there is one more question from Kaushik. Yeah, I'm asking you to unmute. Yeah.
Sir, just continuing on the last part, which Rishabh was saying that we have to wait. Sir, but if we look at the last formula, it is AL minus 1. So
Yes.
when we are getting the output of SL, it's not that we have to wait, in a sense that the output for SL minus 1 is already generated.
Exactly.
And we
That
are
is also
not generating.
That is also true. And I think, yeah, I did, when I answered the last part from Rishabh's question, I did not think it through. So you are right. I mean, if literally we are thinking of sort of waiting till the till the query or attention for that particular time step is done, that is not true, because you are depending on that attention from the previous time step. That is true. And
Yes.
there is no point in sort of basing the output of this time step, on the attention coming from this time step, right? So it may be that also. Okay. Yeah. I mean, I'm not sure whether they use it, but I have not seen attention coming from this time step itself getting used here. No. Yeah. So you are right also.
Okay, thank you. I mean, just wanted to confirm my understanding that it's coming from the previous layer, previous
yes.
times. Yeah. Okay,
yeah.
thank you, sir.
Okay, you can unraise the hand. I'm going ahead with the attention walk. I mean, it is just what we told, just summarizing it with the walkthrough. So you have this encoder decoder model. Again, just forget about these things at this point. Okay. Now you generate these keys from the encoding for each of the, when you are encoding for each time step, when you are encoding this, you generating K1, when you are encoding this time step, you are generating K2 and K3 and so on. Okay. Then when you are decoding first time for this S0, I don't know why I have written Q1 here. Maybe it's a typo. Yeah, that's why I was hesitant in uploading the slides. Yeah, I have to correct these things. Yes, this should be I think Q0. Yes. Okay. Anyway, so you are generating this query, then you are computing this basically the similarity scores, the dot product with these queries keys. Then you are basically doing this softmaxing, that is you are generating this E1, E2, E3. So E1 gives you the similarity score between Q1 and K1. E2 is actually I have just taken the liberty of not writing it as E1, 1, 2, 1, 3, 1, etc. Just, I mean, it's a walkthrough. So the second indices are sort of omitted, but you get the idea. You just get these similarities and you pass it through a softmax layer. You get this softmax value, and suppose this alpha 3 is the highest one, but you are not sending only H3. You are sending a sort of combination of weighted combinations of these H's with these alphas, right? These alphas that you have computed. Now this or this is the A1. You basically use it sort of A0, sorry, that you actually yeah, I have to just I have probably made a mess of these notations and these subscriptions, but yeah, you get the idea. I'll just have to check what I have used. I mean, whether the output from 0th time step is 1 or it is 0. That I need to check. I think it is 1. Anyway, so this then you use it somehow to get the output, and which is basically one way, that the first way that I told, that the output is a function of not only the decoder hidden state but also the attention. And similarly, after you get this sorry, y hat 1, you go ahead with the next time step in the decoder. You get this Q2, you go and compute this softmax, I mean the dot product, the softmax, and similarly you weigh with this HTs, and you generate the YTR and so on. I mean, you go ahead with this. I'm not going into much detail of it. Now, this is sort of the summarization that again, what we have discussed till this point today. I'm sort of discussing. Okay, on the encoder side, you are getting this KT is K of HT. Decoder side, QL is Q of SL. ETL you are computing. Then that is just the dot product. Alpha TL is you are softmaxing it over all the T primes. That is all the T's, and you are computing the AL, right? So then how can you, and then you are sending this weighted combination of these HTs, and how can you use it in different ways? One is to concatenate to hidden state, then use for readout, concatenate as input to the next RNN layer. So this is generating the output. One is concatenating to the hidden state from the previous time step, and concatenating as input to the next RNN layer. So these are basically the summary that of what we discussed till now. Now, let us discuss a little on the attention variance. So that was the basic attention that we discussed. Now, what can be different variants? One is very simple, that okay, K and Q are not just, I mean, it is an identity function. You can say that, okay, K is just the hidden state corresponding to the time step, and Q is also the hidden state corresponding to the time step. Everything else remains same. I mean, it is not, I mean, sort of, we have told earlier that K is, I mean, KT is K of HT. This K is just an identity. That's what I'm saying. So this very simplistic one, it might not, it does not have the complexity maybe, and it might be limited in terms of its representational capacity a little bit. But after that, you do the same thing. That is, you compute the similarity, the softmax values, and finding the weighted combination. That is one variant. The next variant, you may guess that from identity, we are going to only linear. So linear multiplicative attention. What do we mean by this is that the K function is just a multiplication by a matrix. So you are linearly combining all these HT's elements. So it is just WK into HT. WK is a matrix, WQ is another matrix, and you are getting the QL from SL using that. So just the function K and Q, they are linear functions. So what is ETL? You just take the dot product between these two. So it is WKHT whole transpose into WQSL. So it is HT transpose WK transpose WQSL. So you can basically combine these two matrices in some other matrix W. You can just tell that, okay, WK transpose WQ is WE. So when you are learning, you don't need to learn these WQ and WK separately. You can just learn this WE. One single matrix learning is fine. So that is one advantage, that you don't need to learn two separate matrices. And then exactly the similar things happen. I mean, the softmax computation and the weighted combination of the hidden states. Now, this one is almost similar to the basic attention, but the only thing that is different is this V. So instead, so what in the basic attention we are doing, we are combining HT with the alpha TLs, that is for multiplying them. I mean, they're multiplying this HT with the scalar alpha TL, and then for all HTs or for all T's, we were summing them, right? So here what we are doing is, instead of HT, why don't we go for a function from HT? So for K and Q, we have also gotten function from HT and SL respectively. So why don't we go for a function coming from, or a functional representation of the HT when we are sending it? So not directly sending the HT, but you are sending a functional representation of HT. And this V is called, I mean, it is also a learned function. Again, it can be a linear followed by some non-linearity, say ReLU, and so on. So it's some learned function and known as the value. So what is the intuition or interpretation? The interpretation is that now you don't just compute key, rather you compute a key value pair from the input hidden states, because key is a function of HT and V is also a function of HT. So when you are computing K, you are also computing, say, another V. Okay, yeah, say here V1, V2, and so on. And you are just keeping it aside. After you have computed V1, you are just keeping it aside. You are similarly, first you compute these Qs for the decoder, you compute the similarities, you compute the softmax versions. Then when it comes to the time of computing the AL, that is the attention, you are basically then giving these V's instead of HTs. So the interpretation is that you don't just compute key, rather you compute a key value pair, that is both key and value of the input hidden states. During decoding, key query provides the time step with largest similarity between key and query. So when you compute, I mean, this is same as what we were discussing for the basic attention. So key and query, they interact with each other to get the largest similarity between key and query. Ideally, it was that, but again, since that breaks the backpropagation, we are getting the softened version of it. The attention ideally collects the value of that time step from the input. In softmax version, a weighted combination of the input values are taken. So important bit is the value, the term value here. So after you compute the softmax version, you are combining the values, not just the input hidden states. So this is what basically another variant of it. So three variants. One is identity for KQ. One is linear multiplicative, or sort of linear. I mean, linear is coming from there, and this multiplicative part is coming from there. So linear multiplicative attention, and this is the version with the value. Now, before I go to the summary, just one thing I missed telling, why it is called attention. Because you see, you are giving more focus to the one, to the hidden state that is most similar to the query. So you are sort of attending the most relevant part for that decoder state. So that's why it is called attention. And I mean, the mechanism is called attention, and those ALs are called attention scores or attention. Now let us go to the summary. So again, every encoder step T produces a key KT, decoder step L produces a query QL, decoder gets sent within quotes, encoder activation HT corresponding to the largest value of KTQL, but actually it gets AL as this softened version. Now, why is this good? Let us see. Attention is very powerful because now all decoder steps are connected to all encoder steps, direct connection. So you, in a sort of only recurrent connection, this is connected to this, but through all these steps. But here what is happening is that you are getting a direct combination of H1, H2, H3. Okay. So this is now that all decoder steps, and this is true for all the decoder steps, not just this, connected to all encoder steps. Bottleneck is much less important. So bottleneck problem, we have discussed that to say get the output from here or even the hidden state at this time step, you have to rely on this, okay, for getting all the information from the encoder. And gradients are much better behaved. Why gradients are much better behaved? Because remember the problem in RNN for which we went to LST, that is the basically the gradient vanishing or exploding problem. So you are multiplying a lot of small derivatives or Jacobians, and that for the chain rule, and that can give you this exploding or vanishing gradients. The vanishing gradients are more important, as we are saying, I mean, to tackle. I mean, exploding gradients has easier ways to get tackled. So this then gives a shortcut route from this say the higher, I mean the farthest encoder step to this. There is this recurrent connection also, but this is also there. So there will be two gradients that will be flowing. One is via this path and one is via this path. If this is giving you this vanishing gradient problem, at least this might help you not give this. So that is sort of the high level idea when I tell that gradients are much better here. And the other subtle statement that I made, that this path, this recurrent path, can give you still exploding or vanishing gradients, that we will tackle in transformer, we'll be discussing next. So this is the summary, but I would actually stop again from for some questions from Rishabh. I see a raised hand. I'll go to transformer next.
Sir, hello, sir.
Yeah.
Sir, can you explain how the values are generated? I got lost in that.
Yeah, it's basically same as how the keys are generated. So it is just another function. So if you see, key is a function of HT. So from HT you get key. That was just, I mean, maybe the one variant, as I was saying, that WK into HT. Okay. You are getting the value by a very similar process, say V of HT, not K of HT, but V of HT. But again, it's a function of HT. And this one example of this can be, say, some matrix WV getting multiplied with HT. Okay, so just a functional representation from. Any other questions from anybody before I quickly switch to self-attention? Okay, if not, then yeah. Oh, okay. This one, I see. Yeah. Kaushik, you can ask a question.
Sir, sorry, I could not follow, sir, when you said that this problem still persists here. So can you please repeat that?
The gradient part, right?
Yes. You're referring to a problem which persists here and which will be fixed by transformer. So that.
Yeah. So there are two paths that connects. Let me go to this figure. There are two paths that connect, say, this decoder hidden state to this encoder hidden state. This is farthest. One is this recurrent connection. This. I mean, I'm just telling about the back propagation. So when gradient is computed here, then it will go there, and so. But it is also connected to this via this attention, where you have a weighted combination of H1 multiplied with alpha 1, say 3. So when you compute the gradient or you pass this loss via this path, it will be just this alpha 1, 3. I mean, just I'm giving you the crude intuition. It will not be as easy, but it will be a direct shortcut from here to here. Okay. So you are multiplying lots of small derivatives or Jacobians here. So that can give rise to the vanishing gradient. But here it may not be that problem. So for the vanishing gradient problem still persists in this path, but it is taken care of by this a little bit by this path, and so we are getting some good advantages in as far as vanishing gradient problem is concerned. Okay, but in transformer we will actually get rid of these things. We'll see.
Okay.
Thank
you, sir.
Okay, so this was attention. Now, what I'm saying is that if we have attention, do we even need the recurrent connections? So actually, it is continuing with what I said and what Kaushik asks, that do we even need the recurrent connections? We are getting at every time instant in the decoder all the information from the encoder. So can we transform RNN into a purely attention-based model? So if you, actually, let me go and share my laptop here, because somehow in my tab, the latest version is not latest version of the slide is not updated. So let me go there. 1 second, give me a second. Stop sharing. Yeah, it will be much more visually appealing there. So yeah, I can take maybe 5-10 minutes extra today, just so that I can complete this part. Here I was. Sorry. Just give me a second to open this in my laptop. Yeah. And query sharing here. Share your screen. Yeah. Okay. You can see my screen, right? Yeah. I see in my tab. Okay. So do we actually, can we transform RNN in a purely to a purely attention based model? So if you notice carefully, I have sort of removed this RNN, the recurrent connections, right? So from here to here. Now, this has a few issues we must overcome first. So what is that issue? That earlier when we were discussing about structured prediction, so this output was given as input to this basically. So this output was given as input to this this time step. But if I don't have these recurrent connections also, that the hidden state coming from sorry, not the output, the hidden state, this S0 was given as input to compute the S1, or S1 is given as input to compute S2 and so on. But if I remove this, then it is not there, and that sort of hinders this time step to get knowledge from what it has generated. It has during all the time, it has information about what is there in this encoder time step, but what it has produced previous to this particular decoder time step, it does not have. So at time step L is equal to 2, it cannot access S0 or S2. The encoder has no temporal dependencies at all. So this we need to fix. So let us see how can we fix this. So let me just get this annotation tool. This one. Yeah. So so this is the basic self-attention without making distinction between encoder and decoder. So I'm not sort of now at this point, don't think about whether it is an encoder or decoder or something. Just an I mean, it is equally applicable to the encoder and decoder. Let us see. So we have these inputs x1, x2, x3. We are so input from each time step. It can be just the source sentence at this point. Just think about just a language model. Okay, just the source sentence for example. So input from each time step is encoded as this sum ht is equal to this wxt plus b. So a linear function of this x followed by a non-linearity. This is not a recurrent model. The recurrent connection is not there, but it's still weight sharing. So these w's and b's are same for all these time steps. Now, this is sort of the last variant that we discussed on the basic self-attention. So value. So on which we had some question answers also, right? So V is VHT for each time step. Before we just had VHT is equal to only HT. Now VHT is say WV into HT. So we are just using a linear function for getting the value. So the value is computed from this, each of these HTs. And they are also same. That is, these WVs are also same for all time steps. They are shared. Keys, we have outputted keys for all the hidden states of the encoder. So we are computing KT similarly. Now, this is a little different from the encoder decoder architecture. So we had earlier computed the query for the decoder, the SLs, right? But what I'm doing here is now we are computing the queries for this HT also. Okay, so all these HTs, they have three things: V, Q, and K. So value, query, and key, right? And for that also we are taking, I mean, it's the function of HT and it's a linear function of HT. So from WQ, I mean, using the matrix multiplication WQ, right? Now you do the similar thing. So get similarity between key and query. So earlier what you were doing, you are getting similarity between query from the decoder and keys from the encoder. Now your key and query both are from the encoder, and that's why this term self coming. So self attention. It is not attention between decoder, encoder, decoder attention. It's the self attention. And you are doing the same thing, that is for this particular Q1, the particular that is for this time step 1, the query Q1 is sort of getting compared with K1, K, well, I have to read K2 here. Yeah, this is again typo. I have to, I'll make these changes and yeah, upload the slide. So K2 and K2. So you are getting this basically ELT for all the T's. So get similarity between every key and every query, including both coming from the same time step. Now compute the attention scores alpha LT, which is basically this softmaxing these ELTs over all the T's, right? So T's are second sort of subscript. So T basically means the key index. Query is L here, okay? And compute the attention at time step L. So as I said, query is L. So you get these alpha 1, 1, alpha 1, 2, and alpha 1, 3 from this E11, E120, 13. Then this alpha 1, 1 gets multiplied with V1. Alpha 1, 2 gets multiplied with this V2. It should be V2 again. And alpha 1, 3 is multiplied with V3. And there you get the A1. A1 is the attention score, okay? Or compute the attention at time step L. So what you are getting is from time step or at time step 1, you are getting A1. At time step 2, similarly, you will get A2, right? So at every time step, self-attention takes input and produces an output. So at every time step, it takes the input, all these things, always X1, X2, X3. It produces A1. At this time step, it produces A2. At this time step, it produces A3. And remember this, that it does not, this A2 does not depend on A1 or anything from say that for that it needs to wait. So parallelly, all these A1, A2, A3 can be computed. You can parallelly compute this K1, Q1, V1, K2, Q2, V2, K3, Q3, V3. You can parallelly combine all these and you can parallelly combine all this. So there is, since no recurrent connection, you can parallelly combine, and that speeds up the thing a lot because you don't have to wait. It's a sequential, it's not a sequential process. And what is the output? At every time step, self-attention takes input and produces an output. This can be regarded as a layer. So like just say the conv layers, it takes output, gives output, it takes output, gives output. So it can be a layer. So we can build an entire network by stacking such layers. And how is it done, or how will it look like? So you have this X1, X2, X3, you get this H1, H2, H3, you get this, yeah, now it is corrected, this K2, V2, etc. So K1, Q1, V1, K2, Q2, V2, K3, Q3, V3. Now you do this self-attention layer, which ultimately gives this A1, A2, A3, right? All these similarity calculations, softmaxing, weighing, and so on. So you get this A1, A2, A3. You again compute the key query values for these A1, A2, A3. So that's why I have told that for each, for whatever is the input, you can compute these outputs, just the corresponding A1, A2, A3, right? Now, or sorry, I mean, yeah, so and keep repeating this. So the basic idea of getting another sequence from an input sequence is used to get another class of sequence to sequence models known as transformers. So this basic idea of getting another sequence, what is another sequence? From this X1, X2, X3, you are getting A1, A2, A3. Then again, another A1, A2, A3 in another layer. So this basic idea, it can be used to get another class of sequence to sequence model known as transformers. So, but so I think this will be the last slide, yes. But to make this actually work, we need to develop a few additional components to address some fundamental limitations. What are those? One is positional encoding. So it addresses the lack of sequence information. What is the lack here? You are giving, there is no recurrent connection, but in recurrence, you know that, okay, if it is a cute puppy, then first A is processed, then cute is processed, then puppy is processed. So it has some inherent knowledge that, okay, cute follows A, puppy follows cute, and so on. And this order actually is helpful in making a sensical output in terms of, say, the sentences. But there is no way you get this sequence information. So if you compute the A1, A2, A3s for A cute puppy or cute A puppy or puppy A cute, puppy cute A, whatever, they will give same A1, A2, A3. But so the sequence information is lost. So we need to have some sort of ways to basically give the sequence information, which is given in terms of positional encoding that we will see. Then multi-head attention. So allows querying multiple positions at each layer. So it may not be that at each time step, you will be querying only one thing. What is the subject of it? Maybe you can query that, okay, what the, I'm seeing that I need to produce an action. So what action the subject is doing? Or maybe that, okay, what is the second word following the first word? So there can be different queries. So just like crudely, you can think that multi-head attention or different heads are basically sort of similar to different filters or channels in ConvNet. So different channels captures different basically properties of the hidden activations in ConvNet. So you can crudely think that this is basically similar to or parallel to different channels. So that we will see. And adding non-linearities, and this is very important. So far, each successive layer is linear. So in that layer, each successive layer is linear, layered connection. In its previous one, by linear, what I mean is that linear in this VT. So this VT again is computed in a linear way. So WV into HT. So this may be a limiting in terms of its representational capacity. So we will see how to basically increase this by introducing some non-linearities. And this is masked decoding, the last bit. How to prevent attention lookups in the future. So this is also related to this part that, okay, you are giving all at once the inputs for decoding. So X1, X2, X3. But when you are generating the output, what it means, if we don't do anything else, that X2, the output at time step 2 is also dependent on the X3, right? So you don't know that when you are outputting, when you are generating a sentence. So what will be coming at the, say, at a future time step, you don't know. So you need to mask that when you are computing the attention for the present time step. So we will see. I mean, this will not make, say, a lot of sense at this moment, but when we do it, we will see how to do it. So I will actually stop here. Tomorrow, not tomorrow, next day, that is Saturday, we will discuss each of these components. Any questions today? Okay, yeah, Kaushik has some question. Yeah, you can ask.
Yeah, sorry, sir. I'm asking too many questions.
No problem. It's actually good. I mean, nobody's asking questions. You have to ask.
So, sir, if you go back one slide.
Okay, 1 second.
I mean, to the diagram previous.
This one?
Yeah. Yes. Sir, I think everywhere we see this, that it is called as a self-attention layer. But just a nomenclature question, why this is called a layer? Because if you look at it, the entire alphas are calculated separately. The softmax values are separate between H1, H2, and H3. So there is, I mean, I don't understand why it is, called a layer. What is shared really?
What is the last part? What is
really shared? I mean, between, when we call it self-attention layer, why it is a layer? I mean, there is no connection that way between A1, A2, and A3.
The input A1, A2, A3 is connected. I mean, there are sharing. So, I mean, the sort of, or I can say, tell it in terms of this H1, H2, H3, that this H1, H2, H3, they are sort of intermingled to produce A1. That is, it's A1 is a function of H1, H2, H3 all. A2 is a function of H1, H2, H3 all. But I think that is not the right way to answer your question why it is called layer. I mean, layer is just coming from, say, the implementation idea, the abstraction that, okay, if you call it something as layer, then you will just think it as, say, the input and output. And in all the layers that we have seen earlier, we give some input and we get some output. Here also, you can just think it in this way, that, okay, X1, X2, X3 you give, you get this A1, A2, A3. That this A1, A2, A3 you give input, the layer does its own computation and gives you the next A1, A2, and A3. So it is just that. I mean, it does not probably have anything to do with this sharing and so on.
Okay. Thank you.
Okay. Yeah, I have another question from Rishabh. Yeah.
I just want to clear that when we are calculating K1 and K2 from H1 and H2, the weights are same.
K1 and K2, yes, yes, yes. The weights are shared. Yes. Kaushik, you have not unraised your hand. Do you have any other questions? Otherwise, yeah. Okay. Okay. Thanks. So thanks a lot. We will meet again on. Oh, you have another question. So Porimal. Yeah, Porimal.
So, sir, transformer network does not require any decoder?
Yes, 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 yes. It is not the whole transformer. It is just the self attention that.
Oh, okay.
So we will continue on transformer. Yes, it is not the whole transformer. It's much more than that. Yes.
Okay, sir.
Yeah. Okay. Thanks a lot, everyone. Again, we will meet at on Saturday 3 p.m.